So this is a version of 14, and we're going to do W, and it's equal to X over Y plus 2Z. So it's pretty obvious that this is three-dimensional, right? And that's another one, so it's like a fourth-dimensional space. And let's find the partial derivative with respect to X. Then we'll do it with Y, and then we'll do it with Z. And then we'll look at higher order derivatives after this, how you get second and third derivatives. And that's maybe stranger than you think. When you look at this function and you're saying X is a variable, although it looks like an ugly fraction, basically, isn't that just X over a number? You know, if you think the number in the bottom is 42, that's like X over 42. So its derivative with respect to X is actually very simple. Would you agree it was just that? Because the bottom doesn't have any X's in it. Now, if I wanted to do the partial derivative with respect to Y, it might be a good idea to think of this function in that format. Because if I write it like that, can't I do the chain rule on it? Now, if I leave it like that, which is okay, but if I leave it like that, won't I have to do the quotient rule? Right, and the quotient rule would have X on the top and that guy there on the bottom. And that would work, although one of your terms would end up being 0. And it would disintegrate into the answer. But if I think of it like this, it's multiplied by the power, reduce the power by 1, and then differentiate what is inside with respect to Y, which is just 1, and then make it look pretty. Okay. Now, if you wanted to do a partial derivative with respect to Z, which is possible, if you wanted to do it, I would use this format again, and I would multiply by the power. I would reduce the power by 1, and differentiating this with respect to Z gets me 2, and so I end up with this guy. Are we comfortable with that one? It's just a fraction, really. We good? Right.
Don't we need to do it in a certain order for that problem?
Oh, that question isn't what I'm doing. I'm making up my own version of that question. Yeah, but you're right. We're going to do multivariable. We're going to do 2 or 3 partial derivatives, and that is going to be different. So leave that one for the time being. I should put them out of the way, and I'll just make up a nice easy one before we tackle that guy with more complicated versions. We have to look at now how to find higher partial derivatives. Essentially, second and third partial derivatives. You could go higher, but you probably won't, right? Just like a second derivative, f double dashed, and a third derivative, f triple dash. The concept's pretty obvious. Don't you just differentiate the thing you've got again? That's how you get a second derivative. But it's a bit sneakier than that. So let me do z equals x squared plus x cubed y squared. Keep it as a nice, polynomial. Now, if I asked you to find the partial derivative with respect to x, that's a first order partial derivative, you just get 2x plus 3x squared y squared. You're all comfortable with that, right? Now, the notation for second derivatives, at least if you're using this version, is a little bit messy. Do you notice where the 2 goes here and here? Now, technically what I am doing is I'm differentiating this guy with respect to x. So if you wonder where the 2's come from, that delta and that delta gives you 2, and that dx and that dx gives you, I guess the notation could have written that. but you know mathematicians don't like brackets. So if you're wondering why that notation is why it is, it's because of this. Now let's return back to the problem. Second derivative. Well, you just differentiate the first derivative with respect to x, and you get 2, and you get 6x y squared. And if I wanted the third derivative, it would look like that. That would get you 0, and this would get you 6y squared. I mean, if you were going to invent second and third partial derivatives, if you were going to invent or create a method, wouldn't this seem to be a very natural way to do it? Right, find the first derivative, differentiate that, you get the second, differentiate that, you get the third. Totally fine with that. So let's do a little side issue. You have that notation. You also have that notation. If you have a second derivative, the notation becomes that. And I guess for completeness sake, if you wanted to tell someone to do a third derivative, you could do that. And you have to, although it's kind of obvious here, the order is important. Now you might think, no, it's not. I'm doing x, x, and x. Well, I guess in that case it isn't, but that's not how partial derivatives always work. You can actually do quite weird partial derivatives. So let's return back to this guy. I've already got this guy done. What on earth do you think I'm being asked to do when they write that down?
Differentiate y and then x.
It actually means that. So in fact, if you switch the order you just said, that's what it means. Now, do you see that that notation is quite clunky? Because when you see something like that, isn't the idea you do y, then you do x? Because we read from left to right. Well, not everyone reads from left to right. I think the Arabic and the Israel Jewish people read the other way, right? So it's actually right to left from them, right? But that's what this means. It means you find the partial derivative with respect to x, and then whatever that is, you then do a partial derivative of this with respect to y. So if I was writing it out in very long way of writing it, I would be finding the partial derivative of this with respect to y, and the answer I would get here is 6x squared y. I find this notation quite disorientating because it kind of looks wrong. If I asked you to do this, doesn't this notation make more sense? Do x first and then do y second. Do you notice that these two notations kind of disagree with each other in the way that you write them? So it's not just superficial, it is quite messy. So now I'm going to do that one. Now, if I'm asked to do this partial derivative, doesn't that mean do y first? And then whatever the answer is, do x to it. So let's see what that would look like. The partial derivative of z with respect to y, that gets you nothing. And this guy gets you 2x cubed y. If you then do the partial derivative of this with respect to x, you get that. Whoa. something kind of strange happened. Do you notice that those are the same? Even although I chose to do the order, X first, Y second, Y first, X second, right? Although I chose different orders, these are the same. Now, you might just say, it was just a coincidence of numbers, and it could have been, but it's not actually. A French guy, I think there might be an X in his name. You pronounce him Clairaut anyway. That's my version of him. He found out that when you find partial derivatives of this type, they are normally equal to each other. And if they are equal to each other, the reason for it is that Z is a continuous function. So as long as whatever the function you start with is a continuous function, right? It doesn't have funny little water spout vertical asymptotes, right? And it doesn't have, you know, holes in it and plane coming up and plane coming down, right? It's just a normal rolly hill kind of surface. That these two second derivatives will be equal to each other. And the converse is true. If they are equal to each other, then this surface must be continuous. And it's amazing that that is true, because I wouldn't have guessed that these two partial derivatives would be the same, because normally when you do partial derivatives, don't you end up with different answers when you do X than if you do Y? So you would think if you did multiple partial derivatives, they would just get different and more different. But in fact, they end up being the same. Just kind of interesting. So let's try that. So, Sam, give me a power of X.
X to the power of 7/5.
Okay. I'll pick a constant, 3. Emma, give me a power of Y.
4.
Let's do take away. I'll pick the number 2. Keith, yeah. Kathy, tell me a power of E. E to the power of some way X's and Y's or both, whatever you like.
X squared, Y cubed.
Okay, that's bad enough, right? Would you agree that that is a very random function? Looking at that function, would you agree that its domain is any value of X and Y you like? So there's probably no holes in this function. So I'm pretty comfortable that this function is continuous, which most functions should be, at least for you. And let's find that guy. And then let's find this guy. Based on what you could see here, does it seem plausible that if you do the X's and the Y's, and then you switch the order, that somehow or other, it ends up being the same answer? Does that seem reasonable? Well, now that I've told you, but before we looked at that, would that have seemed reasonable? You probably think, nah, if it does happen, it's luck. Well, let's go through the process. You know, I like this notation, 1 and 2, 1 and 2, because it makes it easier for me to remember who you do first and who you do second. So, partial derivative with respect to X, 21 X to the 6, Y to the 4. Take away, with respect to X, you get 2 lots of this guy. And don't you then have to differentiate this guy with respect to X? What does that get you? That gets you another 2X Y cubed. So we have 21 X to the 6, Y to the 4. Take away 4X Y cubed, E to the X squared Y cubed. Beginning to regret this question already. And now we'll do this second derivative. So we're going to do Y next. Right, 4 times that is what? 84 X to the 6 Y cubed. That wasn't too bad. With respect to Y, won't this have to be a product rule? So I'll call this F and I'll call this G. And I'll call the whole thing, including the negative F. That way I don't need to worry about the signs. They'll fix themselves. So it's going to be 84 of this guy, right, plus, okay. F dashed is this guy with respect to y, so that's negative 12 x y squared times e to this guy, plus, which is this fella, the derivative of this guy, which is this fella. And since we are doing it with respect to y, another 3x squared y squareds. So what does that get me? 84 of this guy, negative 12 of this guy, and that is negative 12, and that is x cubed, and that is x y to the 5, all over that guy. Well, according to Clairaut, z of yx squared, z of yx will be the same thing. But I'm not going to do it. You can do it yourself. When you've got time and you want to have a shot at it, try it out. But provided I did this right, that guy will be the same. Now, Clairaut figured out that if z is a continuous function, then you can find these two partial derivatives and they will always be the same thing. But he discovered something even bigger than that. Can you imagine doing a partial derivative like this? Now, that means you do x first, whatever the answer is, partial derivative with y, then x again, whatever that answer is, x again, and then lastly, oops, that's 4, and then lastly a 5. If your function is continuous, Clairaut discovered that as long as it's the same 5 guys, you can do them in any order that you like, and the answer will still be the same answer. That's even more unrealistic, but yet true. Right? Now, can you imagine doing a 5th derivative? Right? Nobody really wants to do 5th derivatives, but imagine that you had to. Then what Clairaut says is, you can choose whatever order you do the 5 that you like. I'll show you why that could be useful. Suppose I had that function and I wanted to find that second derivative. If I try to do this with respect to y first, can you see that I am going to be spending a heck of a lot of time trying to figure out that guy? But since I know Clairaut's theorem, I can say, well, if you want that answer, I might as well just do this one. Now, why is that one going to be easier? Well, let's find out. If you do a partial derivative of all of this with respect to x, don't you just get 2xy? Because doesn't that become 0 with respect to x? And then when you do it with y, oh, do you see how easy that particular second partial derivative was because of Clairaut's theorem, which essentially says, as long as your function is nice, continuous is basically nice, you can choose to do your partial derivatives in whatever order suits you best. So if you're looking at a question, you're thinking, I don't want to do the y first. That's ugly. I want to do the x first. Then go ahead. Do the x first, and it'll be fine. You like Clairaut? Not saying I like many French people, but I like Clairaut. He did a good job. French, this is not an insult, this is actually a compliment. There was a period in time, at least two different periods in time, where some of the best and cleverest minds were French mathematicians. Pascal, Clairaut, Euler, no, Euler was German actually. Try and think of some others here. Well, there was a whole bunch of them, and they came out with some really cool stuff. And there was another period of time, actually, during one of those times, the Germans were really big as well at mathematicians, and Euler and Leibniz and mathematicians like that, they came up with some really cool stuff to do with calculus and number theory. And Gauss, there's another guy. I think Gauss is German. Really good. And then there was another part of history where Scottish and English mathematicians were out there. So Newton with calculus, Maclaurin's theorem, right? All those good stuffs. Big bunch of ones. There hasn't been a time yet when mathematicians from America had a big time. So maybe one of you one day will become one of those exceptional brains and turn into some really cool stuff, you know, and generate some really interesting math. That would be nice. Okay, I'm looking for some second derivatives here. Let me find something interesting, not just stuff. Yeah, it'll do. This is question 19. T is e to the negative 8r cosine of theta. And we're being asked to find four different second order, second partial derivatives. Right. Now, let's think about how we could minimize our workload. So I'm going to start by finding that guy. Another way of writing that guy is this. Well, if you differentiate this with respect to r, you get e to the negative 8r cosine theta, right? Because it's multiplied, it's still there. And times what else? What's missing from this derivative?
-8.
Right, so I'll stick it at the front. Now, since I know this guy, I'm going to then use him to get this guy, and I'm also going to use him to get that guy. Do you see? You don't do that again to find these two, right? Don't you just do it once, then you use this answer here and here. I would think most of you would do that without thinking, but it is, you know, a reduction in your workload. So if we do this guy, are you happy about why it turned into positive 64? Great. Okay. Now, if I wanted to do this fella, then won't I use this answer and just differentiate it with respect to theta? So you take this guy and you go negative 8 e to the negative 8r. Differentiate a cosine gives me a negative sign. And so I end up with that guy. So we'll put a little asterisk next to our answers. We've got this one and we've got this one. What about that second derivative? If I make the assumption that this is continuous, and I'm pretty sure it is, there's nothing that weird going on with this function, what would I be able to say about this second derivative?
That it's 8e to the negative 8r sine theta.
Can you imagine this was a really, really ugly function, but it was still continuous? Wouldn't it be nice if you could at least cut your workload down and say, well, once I found this one, I know what that one is. And the last one, you can't really do much except find t theta and then do double theta. So let's see. If you differentiate this the first time, you get a negative sine theta. And if you differentiate this with respect to theta, you get negative cosine theta. And that is essentially the end of that question. And now I can tell you how to spell Clairaut, because they mention it in one of the questions. And I was miles away. So if you want to look him up, there he goes. This one is similar to question 17. And we're being asked to find this fella and this fella. Okay, so here's my function. Partial derivative with respect to x is basically a power rule, followed by another power rule. If you do it a second time, power rule, power rule. If you do it a third time, 336. Power rule, 210. Power rule. Now, if you wanted to do this guy, I could use some of these answers to reduce my workload. What order do you think it might be more advantageous for me to do this third derivative?
X, Y.
And can you all see that that's a good choice, because can't we already use that answer to, reduce our workload, right? Because we already know what XX is, right? And Clairaut says as long as it's continuous, you can do them in any order you like, as long as it's the same number of X's and Y's. So if I wanted to get X, Y, which is the same answer as what that would be, I would just take this answer and do it with Y's. Good grief, 450 and 54, 506, I believe. And 320, 336. Nobody's been telling me I've been screwing up. Have I been screwing up?
It's 504, not 506.
See? Thank you. Well, we assumed that when you go back and look at your notes that you might want to double check some of the calculations just in case you skipped one and thought it was okay. So I like Clairaut. Anybody who makes your life easy in math is good, isn't it? So if you're going to do partial derivatives and there's a little, a little way out, that is, I think that's a good thing. Pretty comfortable we've covered. Oh God, no. Uh-oh. I just looked at a question that I haven't talked about. I was about to say I think we've pretty much covered all the good stuff, but we haven't. We haven't done inverse sines, but that's not the major thing, but that's true. We haven't done inverse sines. Nor have we done evaluating a partial derivative at a particular point. Although even if I hadn't covered that, I would hope most of you would say, well, I think I know what you're going to do. Would you agree that I'm going to find what this is? And then I'll plug x equals 3 and y equals a 6 and get the answer. And if you were thinking that, you were right, but I should cover it. It has got other quite interesting features. The partial derivative of this with respect to y is not clean. Would you agree that it is at least a product rule with a really ugly g? So keep your eye on that fella. So it's going to be f dash g plus f of g dashed. And that guy there, with respect to y, is 1. And you leave the other guy alone, so that's not too bad. And now the really messy one. If you differentiate this with respect to y, you first have to know what is the derivative of an inverse sine.
Is it 1 over 1 plus x squared?
That's an inverse tan, but you're darn close.
1
Oh, is
over
it the square root?
Of, yes, of,
X squared plus 1?
right? Forget the pluses.
1 minus x squared.
Yes. Isn't that the kind of guy that you should have written down somewhere so they can go hunting it? Because it's not a kind of typical derivative that you do tons and tons of, right? Everybody knows e to 2x, e to 7x. Now, we have the added issue of it being a chain rule, right? So it's not an x, but an xy. But that's still doable, isn't it? 1 take away xy squared times the derivative of xy with respect to y.
X.
Now, all I'm doing here is trying to make it pretty. Are we okay with that answer now? You comfortable where all the pieces came? Now, to get the partial derivative at 3 comma a sixth, it's going to be the inverse sine of 3 times a sixth plus 3 times a sixth over the square root of 1 take away 3 squared times a sixth squared. So that's going to be inverse sine of a half on the top. That's a quarter, right? So that's 1 minus a quarter is 3/4. We got a lot to do. This is not the right answer as far as style points go, right? And numerically, it's the right answer, but not as style points. So what angle has a sine of a half? Because that's what inverse sine of a half is. So what angle in radians has a sine of a half?
Root. Root 3.
Pi over 6.
Right, so there's going to be a 1 there, there's going to be a half there, there's going to be root 3, and it's pi over 6, correct. And let's do, here we go. Let's do a double check. Now, I'm going to make sure I'm in radians because we're not, so I'm glad I checked. No, actually, now I think about it, let's go back to degrees. Inverse sine of a half is 30 degrees, and 30 degrees is pi upon 6. So I'll basically let the calculator figure it out for me. Plus 1/2. Okay, square root of 3/4. Can't leave that hanging, right? That's ugly, ugly, ugly. Any suggestions for a way to fix it, a way to write it a little bit differently?
Root of 3/2.
Now, this is probably a long-winded way to do it, but isn't that the same as a half times the reciprocal of the bottom? Which means you've now got that. And if you want to be really fussy about it, you've got that. Are you happy about that? If I'm being extra fussy, can I even do that? I would be quite happy with that. I'd be very pleased with that, and I'd be going, wow, you really went the whole road with that one. Who knows where WebAssign ends up being, right? It's a lucky dip with them, right? So keep making it pretty until you can't think of anything else to make it prettier with, right? Do the best style point you could, and hopefully it will be happy. It will like it. So for the last thing I'm going to do today, I'm going to show you an application of how using partial derivatives can find things that you might want to find. Way back in Calc 1, can you remember doing implicit differentiation? Can you remember that? And can you remember how ugly and messy and time-consuming it could be if you had a really big expression with lots of pieces in it, like this one? Wouldn't it be nice if there was a simpler, quicker way to get that answer? Well, let me show you. First thing you do is pretty cosmetic, but you do it anyway. You rewrite your implicit function with everything equals 0. This fella here is called capital F of xy. That is going to be your multivariate function, right? This guy here. And the derivative, right, because that's what you want, right? The normal Calc 1 derivative, dy by dx, right? Not your partial derivative, your normal Calc 1 derivative is that. And let's see what that looks like. It's a negative of 3x squared y squared, nothing, 2x. On the bottom, this guy with respect to y, so what's that? 2x cubed y minus cosine y. Was it not quick? That took, what, less than 1 minute to find the derivative of this implicit function. Right, less than a minute. There's your answer. Okay, the whole thing's got a negative around it, but you could write that in various ways. I think that's impressive. Why didn't we tell you that in Calc 1? Because there's a famous saying, a little knowledge is a dangerous thing. And if we had told you that, you would be doing partial derivatives all over the place in places that was never intended to be used in Calc 1. And you know that wouldn't be good news. And then you might go into Calc 2 and continue to damage your math by using that same technique. Now that we're in Calc 3, do you see that we can show you these because you now know there is a distinct difference, isn't there, between Calc 1 derivatives and multivariate partial derivatives, right? There's a very distinct difference between the two, even although they may superficially look like they have X's and Y's in them, the way we treat them is quite different. That is a pretty cool thing, isn't it? And there are all sorts of goodies that we haven't told you yet. So as you go through your math career, you'll find all sorts of little interesting things. If you want to cheat a little bit, I'll just off the top of my head. I think that's how you pronounce him, another French guy from that same time period that the French were doing things called de Moivre's theorem. And what he does is he tells us that that is true. And what that allows us to do is find all the fancy trig identities, sine of 2 theta, cosine of 2 theta, pretty much all the identities that you have to memorize can be created by manipulating one or more of these equations together.
Is that I as in imaginary?
It is indeed. And what he discovered was that sines and cosines were connected to E. Remember the power rule? Remember when we did the powers? And remember that the power series for exponential for e to the x was very like the sine and the cosine stuck together. That was not coincidence. That is a consequence of this rule. And what he also went on and discovered, because he spent a lot of interesting work on complex numbers. So you thought complex numbers were that kind of weird thing you did in Math 99 because some quadratics don't work as real numbers, so you stick an I in. And that's scratching the surface. There's a whole chunk of math to do with nothing but the complex field. And it comes up with some phenomenal stuff. Remember that 2 by 2 matrix I was talking about? That comes out of a version of his theories. So he did a whole load of cool stuff. So you're going to find all sorts of things that we don't tell you until you're mathematically ready to be told them. Right. There are some things that you don't need to worry about. 0 times 1 is still going to be 0, right? We're not going to tell you in a year from now, well, it's really this other number, but we didn't want to tell you that because we don't want to scare you. Okay, so have a nice day, everybody. Say hi. I'll hang about at the end if we have any questions. Otherwise,
Can
I'll see you on
touch a
Monday.
little bit on the hyperbolic, cosine, and sine derivatives? Because there's one question that covers some of that.
That shouldn't have been in there. What darn question did I put hyperbolic in?
It was one that had a bunch of choices, so you were supposed to do the derivative things.
Okay, I can tell you off the top of my head, the hyperbolic sine function, its derivative is the hyperbolic cosine. So sine h of theta, its derivative is cosine h of theta. And cosine h of theta is still positive sine of h theta. So it's not quite the same rule. Everybody's positive, which in a way makes it easier. So that'll take care of it, I would think. But we haven't done, Calc 1 never did hyperbolic, Calc 2 never did hyperbolic. If they did, it was very superficial.
It was number 15. 15.
So when you get to 15, just remember that the derivative of a hyperbolic sine is a hyperbolic cosine, and a hyperbolic cosine's derivative is still a positive hyperbolic sine. There's even a hyperbolic tan and secant, but don't go there. Oh, and by the way, do you know a hyperbolic function? He's described in terms of e to the ix. If you look up the definition. So de Moivre is almost guaranteed to be the guy that went into that. Okay, bye-bye, guys. I'll hang about, as I said, for any questions. Okay, Madison, Sean, Douglas, or Sam? Who's got the question? Anybody?
I don't have one.
Okay. Sam?
I just have.
Oh, Sam, Sean,
Oh.
sorry.
All right, sorry. I just have a question about next week. So, like, we got to number 20 today on partial derivatives, and
Yeah.
we already went over multivariable functions and limits.
Yeah.
And
We've
that,
only
like,
we've got a little bit more. I never actually finished everything that I wanted to do in that section, but that's fine. So when you come back on Monday, we've got a little bit more to do in 14.3, but it's a special subgroupy derivative, so we'll wait until we do that. And then we've just got, I believe, the chain rule. Is that all?
oh, all right. All right, well, thank you.
And I don't know if I put it up, but we do have one more section called the chain rule.
Oh.
I'll make
Yeah,
sure I
there's only
put it up.
3 things on the website.
Right, so there is a fourth one. It's called the chain rule.
Right.
So we'll put that up. And chain rule will probably take about 2 days. So about Wednesday, I would, we should be finished. That gives us a couple of days revising for final and getting ready for, tidying up the loose ends and so on.
Mm-hmm. And is there a chapter 14 test on next Monday, and then there'll be a final, like,
yeah,
that week?
But the last test, I only use the best 4. So if you've got 4 really good ones, you don't need to turn up for the last one. You might want to keep that and just revise for your final.
All right, yeah, for sure.
If you've got a really bad one or one that you think, I could probably do a bit better, then you should do it just in case you improve your grade.
Okay.
But you're right, there is one last test to go and it will be on their chapter. Madison, you got a question or you just forgot to check out?
I have a question about the limits homework.
Okay, what you got for me?
For question 4, I'm having difficulty figuring out how to.
Right, so it's probably an XY tending to 0, 0. Agreed?
Yeah, it's XYZ turning into 0, 0.
Oh, it's a triple. That is interesting. Let's rewrite that again then. It's an X, Y, Z turning into the origin, essentially. And what's the function? It'll probably be a fraction.
It's XY plus 6YZ squared plus.
Did you say
9x.
Z there? You did.
Yeah.
You said. So it's XY plus 6YZ squared, right?
Plus 9XZ squared.
On the top?
Yeah.
Okay. What else?
And then the bottom is x squared plus y squared plus z to the 4.
Okay. So what I'm going to do is I'm going to do 3 versions of this guy. I'm going to do the version where x goes 0. And that means I already fixed these 2 guys, the other 2 guys as 0. And then I'm going to do an equivalent y1 and an equivalent z1. And so when I do the y tends to 0, I'm also going to at the same time fix the other 2 to be equal to 0. And when I do the limit as z tends to 0, I'm going to do these guys. Now the reason I'm going to do that is if these 3 answers disagree, in other words, if 2 of them say it's 0 and 1 of them says it's 4, that means this limit does not exist. Right? So let's start with the first one. If you make y 0 and z 0, this integral becomes the limit as x tends to 0. Right, if you make y 0 and you make z 0, you get 0 on the top. And if you make y 0 and you make x 0, you get 0 over, what do you get here? 0 over x squared. Agreed? And that's very problematic. Do I get some better with the y's? Oh, I see what's going to happen. If I do it with the y's, that's going to get me nothing, nothing, nothing. Ah, interesting. Because these are all indeterminate forms, aren't they? Let me go look at that one. Because I was hoping to get 0, 1, 2, in which case it would be a does not exist. Or 3, 3, and 3, in which case I'd be able to pretty much assume that the limit was going to be that given number. Have you tried a DNA yet, just to see if that's what the answer ends up being?
Not yet. I tried doing the little watch option to see what they did, and they got a number for it.
Oh, they did? Interesting. So did they do some kind of X equals Y equals Z kind of thing?
I think the one they found the answer for, it was like X equals Y, Z equals 0, something weird. I don't remember off the top of my
okay,
head.
so they just permed it in some weird way. Okay, so that sounds to me like that might be what they're doing this second time. I'm having issues with open windows here. Okay, let's stay signed in. I'm just going to find that guy. He was under limits, and it was question 4. Let's bring up their solution, see how they tackled it. Okay, they did. Well, let me just show you. That's the easiest way of doing it. Can I make this bigger? Right. So the limit doesn't exist, which I was pretty much, the minute I saw that, I was kind of sure that that's what was going to happen, but that doesn't mean that it has. So this is what their solution looks like. Let me try and explain what the heck they're doing, right? So here is the function, or at least a version of it, right? I think you had a 9 here, but that really won't matter too much. Now, if you do this guy, you get the 0 over x squared. And there isn't, well, I guess it is true, although I wouldn't phrase it that way. They're saying that this answer is 0 as long as the x isn't 0. That's pushing it, but okay. So they're saying that the guy I had question mark over, they're saying as long as you don't make x 0, the answer is 0, which is really pushing the math. So this along the x-axis is 0. So they're assuming that the first answer I gave, instead of putting question marks, was 0. And then they did this. They make the first x and the y both the same thing, and they made the third guy the z0. And when you do that combination, you get a half. So I'm going to go back to your question and just kind of show you what I hope is a better way of looking at that solution. Essentially, what they're going to do here is they're going to...
We can't see your
Oh,
paper.
I haven't written it yet. But essentially what they're going to do here is find different pathways to the origin. So normally the simplest pathway is just make the other two 0 and make x on them. But I could do anything I like. For instance, they've decided to find the limit using x and y being the same. So that's like you're homing in on the origin, but you're just making the x and y the same number. Now, if you make the x and y the same number, this becomes x times x. This becomes 6x z squared. And this becomes 9x z squared. And this guy is x squared. This guy is x squared. And this guy is, well, essentially z squared. Now, you make z 0, you get x squared, nothing, and nothing. And if you make z 0, you get 2x squared plus nothing. You get x squared over 2x squared, so they come up with a half, which is fine. Now, I don't like their particular guy, so I'm going to pick a different guy. Suppose I decide, just because I want to make x 0 and do a y version. So I'm just deciding that the y coordinate and the z coordinate are going to be the same thing, right? Well, what would that look like? Right, you'd get x, y. You'd get 6y, y squared, which is what, 6y cubed. And you'd get 9y, y squared, which would be what, 9y cubed. And on the bottom, you would get x squared, y squared, plus y squared. And now I'll make x 0, and that's nothing. This guy and this guy is 15y cubed.
I think
This is nothing.
I think
Sorry?
so. I think instead of 9y cubed, I think it's 9xy squared.
This here. Oh, is x y squared. Gotcha. Oh, not here. This one here should be 9x y squared. Okay. So what does that give me? 0 then, because x is 0. Nothing and 2y squareds. What would that give me? Is it 2y squareds? Yeah.
So it would be 15y cubed instead of, it would be 6y cubed instead of 15y cubed on the top,
Okay.
right?
Yeah. Now, if you cancel that out, do you see that you get 3y? I know I'm making lots of mistakes, but what's that going to be? Isn't that going to be 0? And if the answers are different, it means the limit doesn't exist. I guess, couldn't I have done x0x? Couldn't I have done that combination? 00z, that combination. Right, just pick two of them to be the same and make one of them to be 0 and find a limit in that case, because what you're essentially doing is reducing this into a one variable limit. And if you can reduce something to a one variable limit, it's normally quite easy to find out what that limit would be. And if the limits are the same, then that's a good indication that it converges to whatever that number was. But if the two limits are clearly not the same, then that means it does not equal. Did that help, Madison? It's a sneaky trick, but that's kind of what you have to do.
Yeah, thank you.
Right. Do you know if you're doing a 2D one, you could do x is 0 and y is 0, and very often that takes care of it. But see if that doesn't work. Couldn't you do an XX becomes 0, 0, or a YY becomes 0, 0, and see if you can get anything out of those two combinations? And any other questions?
Yes. So, do you know when you're going to release the answers for test 4, so we can see what?
I can do that as soon as you leave, because I forgot. Any other questions?
Is question 10 the one we're going to be going over tomorrow for 14.3?
Does it mention the word, oh God, does it mention the word implicit differentiation or something along those lines?
Oh, yeah, that's 11 and 12.
Yes. So those are the ones I haven't covered.
Okay, sounds good.
Okay.
Thank
Okay,
you.
well, you're welcome. Bye-bye, guys.
Thank you.